Welcome back, guys. We are going to be doing some more logic puzzles on the Brilliant app. Okay, next up we have Euler and Venn diagram basics. Logic isn't all about complicated multi-step deductions or solving intricate word puzzles. Sometimes logic can be as simple as a diagram used to visualize what we know about a domain. In this lesson, we will cover two such diagrams and see how they can be used to map out logical statements and deductions. Consider the following diagram, which displays some information about certain types of cat. What kind of cat do you think the star location indicates? So it's a cat that's black and not fuzzy. Cats who are black and not fuzzy. The previous diagram is an instance of a Euler diagram, which visually represents relationships between categories. For another example, we know cats are mammals, so we can make a broader diagram illustrating this fact. Since all cats are mammals, anything that falls under the category of cats must also fall under the category of mammals. We represent this by placing the cat circle wholly within the mammals circle. Not all categories are so clear-cut, however. Consider the category of things with eyes. Cats have eyes, so we may be tempted to put things with eyes category surrounding the cats within mammals. However, plenty of non-mammals have eyes too, so this won't do at all. If we want to add frogs to our diagram, for instance, we need to make sure things with eyes can include them, even though frogs aren't mammals. This means we need to make the circle cut across the mammals category boundary like so. You may notice that the proportions of the category may seem off. Don't worry, this isn't saying anything about eyeless cats and frogs. The goal with a Euler diagram is only to express the relationship between different categories and not their relative sizes. Here we have a Euler diagram representing pet preferences. For example, someone in the upper right only wants cats as pets, whereas someone in the center is fine with cats, dogs, birds, and fish. Not every combination of possible pet is accounted for. Which of these combinations is not included in the diagram? Cat and bird only, cat and bird only. That one. I won't bother looking at the others because that one's definite unless we can choose multiple. Nope. A small ice cream company sent out a survey to customers asking them about their ice cream preferences. The survey asked people to check off all of the flavors from the list that they like. Then the data was gathered and a Euler diagram was made from the results, where each respondent can have their response represented somewhere in the diagram. If you were to look through the surveys, what is the largest possible number of flavors that any one person indicated a preference for? So this circle only contains one more. This circle only contains one more on either side. Same with this one, and this one's one. So 2 is the maximum that one person can say. A Venn diagram is a Euler diagram where every possible combination is visually accounted for. This Venn diagram representing 3 categories, cats, mammals and frogs, has 8 distinct regions. The exterior region, 8, represents things, for example spiders, that aren't cats, mammals or frogs. Note that although a Venn diagram shows every combination of the categories, some or even almost all of the regions might be entirely empty. We can represent this idea by crossing out these portions. In this example, since frogs aren't mammals or cats, and all cats are mammals, the regions indicated below will be entirely empty. In this Venn diagram, each circle represents people who like a particular movie genre. horror, comedy, or romance, and romance. However, the labels have been erased. We don't know which circle is which. Suppose Sarah, who likes horror and comedy but not romance, is marked with a star in the diagram. Which genre must circle C represent? So she likes horror and comedy but not romance. Here is a Venn diagram that represents different attributes a shirt can have. Dark orange striped. What would a shirt indicated by a star on the diagram look like? It wouldn't be orange striped or dark. This Venn diagram represents food preferences. How many of the 8 marked locations indicate people who like exactly 2 of the 3 foods? So exactly 2 is 3, because the one in the middle is exactly 3. So 3. In this lesson, we have seen how Euler diagrams can be used to visually display information about a variety of different categories. Venn diagrams, a special case of Euler diagrams, are especially useful when considering all of the ways in which various categories under consideration can overlap. Still, you may be wondering how Venn diagrams are relevant to the study of logic. In the next lesson, we will answer this question by seeing how we can use Venn diagrams to model logical statements. So far, we have looked at Venn diagrams exclusively as a way to model information about groups such as t-shirt designs or people's movie preferences. How then can we apply this to the study of logic? Consider a Venn diagram representing 2 categories of animal, bats and nocturnal species. Suppose we are using this diagram to model the statement, all bats are nocturnal. Which region of the diagram must be empty? 1. For this lesson, the standard way to notate that a region is empty will be to cross it out. With the statement all C are D, we want to cross out any C that are not also part of D. So with all bats are nocturnal, we cross out anything in bat that is not also part of nocturnal. Here we have a diagram representing 3 types of fruits, apples, bananas, and all tasty fruit. Suppose we want to use the diagram to represent the statements, all apples are tasty, all bananas are tasty. Which regions would you cross out to represent these statements? So we'd cross out 1, 4, 7, and 8. 8 isn't an option, so 1, 4, and 7. In this diagram, comparing meeps and blue things, the intersection between the 2 categories is crossed out. What can we conclude from the crossed out section? That no meeps are blue. This is an example of a statement with the form no C or D. With these statements, we cross out any region on the diagram where the categories intersect. Consider again the fruit diagram from earlier. Suppose you've had a change of heart and now hate apples and bananas. You now want to represent the statements. No apples are tasty. No bananas are tasty. Which regions would you cross out? Okay, this is a bit more complicated. Right, I think it's 2 and 6, but it might be 2, 3, and 6. But there isn't anything to say that there's no such thing as a crossbreed between a banana and an apple. So I'm going to say 2 and 6. I really don't know about 2, 3, and 6. Let's try 2 and 6 and then see if it... Incorrect. 2, 3, and 6. Yeah. Yeah. So I should have crossed out 3. I knew I should have crossed out 3, but like I say, I didn't know if there was a crossbreed between bananas and apples because in this particular situation, I don't know if that thing exists. But yeah, I should have used common sense and put 3 in as well. That's fine. Then again, going back and looking at it, 3 is part of apples, and 3 is part of bananas. So yeah, I should have definitely crossed it out. Yeah, fair enough. Fair enough. Suppose we want to use a Euler diagram to model the statements. All Lannisters, hey, Game of Thrones. All Lannisters pay debts. Some Lannisters are dead. I think all of them are. Sorry. Spoiler alert. You have come up with 4 potential diagrams to represent these statements. In each of these diagrams, every region contains at least one element. None of them can be crossed out. So all Lannisters pay debts. Some Lannisters are dead. So all the Lannisters have to be in the pay debts, and some of them are dead. So it's got to be B, hasn't it? All Lannisters pay debts. All Lannisters. Yeah, it's got to be B. Some indicates that a portion of the diagram is filled rather than crossed out. We'll be representing this with a check mark on the diagram. Suppose we want to model the statement some aliens are green on a Venn diagram of the categories aliens and green. Which portion of the diagram should have a check mark? Some aliens are green. Well, 2. 2 is definitely a check mark. Is this a trick? Am I missing a trick here? Some aliens are green on a Venn diagram. Some aliens are green. Is it going to be 1 and 2? Because some aliens are not green? So, I don't know. Let's do 2 only. Right, brilliant. Thought it might have been a trick question. Been playing too much 1% Club. Be careful when adding check marks to diagrams. Suppose we add in a third category, blue, in the previous diagram. With a statement like some aliens are green, we can't be sure whether 3, 6 or both get check marks. To resolve this and figure out where to put the check marks, you'll need to think about them in combination with other statements. Some aliens are green, no green things are blue. When modelling both of these statements with the new diagram, what regions will have a check mark? So no blue things are green. So it can't be 3, so it has to be 6 alone. So far we have only covered the case where we have some statements that we use to put check marks and X's on diagrams, but we can also go the other way round. Consider this diagram with the markings already filled in. Based on the diagram, which of these statements is true? Some mystical things are ancient. No. Dragons are sometimes ancient, but always mystical. No. Some mystical things aren't dragons. No. Dragons can be mystical or ancient, but not both. Yeah. To summarise the major points from this lesson, all C or D indicates any C not part of D may be crossed out. Yep. No C or D indicates that any C that is part of D may be crossed out. Okay. Some C or D indicates that the intersection between C and D must be filled. In the case some, there is more than one region between C and D. A check mark can potentially go in either or both, but without more information, it's impossible to know. Okay. Right, spot the fallacies. This lesson has a series of truths mixed with fallacies. For each problem, the validity or invalidity is determined solely by the statements given. We are judging the validity of the therefore statement, which claims a particular statement is always correct. It may still be possible the conclusion is true, but there isn't enough information to justify it, meaning the argument is invalid. Consider the argument. All cats are fuzzy. All fuzzy all fuzzy things are warm. Therefore, all cats are warm. All cats are fuzzy. All fuzzy are warm. All cats are warm. Yeah. All sheep are soft. All woolen things are soft. Therefore, all woolen things are sheep. Right. All sheep are soft. Therefore, all woolen things are sheep. No. Woolen things, sheep. Soft. I'm pretty sure. I'm expected to get tricked at some point, which is why I'm taking my time a little bit. No grooves are white. No white things are dark. Therefore, all grooves are dark. No grooves are white. No white things are dark. Right, in a minute. My brain is collapsing. No grooves are white. No white things are dark. Therefore, all grooves are dark. Well, I mean, yeah, kind of. But that's only if there's two options, white and dark. There might be other options. Blue, green, orange, purple, pink. I think it wants me to put valid, but I don't agree because that doesn't necessarily mean that they're dark. Ah, there we go. So yeah, I should have just gone with my instincts. So no white things are dark. No grooves are white. No white things are dark. There is still a groove portion that does not intersect dark. Therefore, the statement all grooves are dark is false. This is known as an illicit negative. Right, so basically I was saying that there's going to be some grooves that aren't dark, but I think this is saying that there's some... Yeah, I think it's saying... Yeah, it's saying exactly what I said, so I should have just trusted logic. I thought it was trying to make me put this based on the information given. Yeah, I should have just trusted logic. All dragons are young. All winged things are on Mars. Well, none of them have got anything to do with each other. Therefore, all dragons are on Mars. None of them have got anything to do with each other. All vampires are immortal. No quiet things are immortal. Therefore, no vampires are quiet. That is true. All chocolates are tasty. No donuts are chocolates. Therefore, that can't be true. Donuts are definitely tasty. Right, all chocolates are tasty. No donuts are chocolates. There's still a section where they overlap. Right, some frogs are Kermits. All frogs are green. Some frogs are Kermits. All frogs are green. Some Kermits are green. Oh, I'm going to need to use a pen and paper. I need to draw this flaming diagram. I can't do this in my head. Right. Circle, circle, circle. In a minute. I don't even know how to draw a flaming diagram. Hopefully I've got one at the top of the screen. No, I haven't. God damn it. I can't even think how you draw the damn thing. Does that overlap with that? And that overlap with that? Oh, I'm making a right mess of this on my paper. Right. Okay. So, some frogs, so frogs here, some frogs are Kermits. Tick. All frogs are green. Tick, tick. X. Therefore, some Kermits are green. Tick. Yeah. All widgets are round. Right, let's use the diagram again. All widgets are round. So I've got widgets, round, and smooth. All widgets are round. Okay, so all widgets are smooth. Therefore, some smooth things are round. I'm confused. Right, all widgets are round. Some smooth things are round. I've got a feeling I'm gonna get this wrong. I don't know why. No, according to the diagram, this is right. Yeah, it's that. What? Come on! I've just drawn the diagram. Go on then, show me. All widgets are round, right? Why is there an X and? Oh yeah, of course. And then yeah, if the assumption was made that every portion of the Venn diagram has at least one thing in it, we could have used the central portion to indicate some things are smooth and round. Yeah, however, since we can't assume widgets... Shut up. We can't assume that widgets exist at all. Are you seriously going to throw that at me? We don't know if there is a check needed in the... So you're basically going to tell me I'm wrong because I can't assume that it exists. So doesn't that apply to the Kermits and the frogs and the chocolates and the donuts and the vampires and the dragons and the Groos and the whites and the darks and the sheep and the woolen and the cats and the fuzzy? Shut up. You can't go and make up the rules as you go along. This is known as an existential fallacy. I mean, to be fair, I drew the diagram wrong anyway, so I accidentally left these as ticks. I should have crossed them out. Right. That is the most ridiculous argument I've heard in my life. It might not exist at all. We might be living in the Matrix. Oh my God. All right. No, well, now I don't know how to answer this because this pizza, it might not exist, and cheese might not exist. Round might not exist. We might be living flat Earth. Oh God. Right. I'm not I'm not happy about this at all. That's just made me question everything that I'm ever going to read. Is it true? Does it exist? Right, I'm going to pretend that this widget question never happened and that everything is actually existing because that is just absolute nonsense. I'd have to say everything is wrong or invalid because you can't assume everything exists. Right, okay, let's carry on. Some pizzas are round, some pizzas have cheese. Therefore, some round things have cheese. I should be able to do all this in my head, but I don't trust my head anymore. I need to do Venn diagrams. So, some pizzas are round, some pizzas have cheese. Therefore, some round things. No, it's saying some, not all. They might not interlock. Yeah, I think it's invalid because of the sum. Hey, let's see the explanation. To demonstrate the argument being insufficient to be true, let's do a possible fill of the diagram that will still allow the conclusion to be false. Note this is a possible way to mark the choices. Some pizzas are round, some pizzas have cheese. As there is still no check mark between round and cheese, we definitely can't say that the conclusion is true. Yeah, so it's the fact that it says some and not all, so I'm happy about that. In this lesson, we went over some common logical fallacies that are easy to fall into. Moreover, we used the Venn diagram. Yes, I did use the Venn diagram. I'm glad I've got paper and pen. I could obviously do it on the computer, but it's just far quicker doing it with paper and pen. Okay, happy days. All right, let's move on to the next one. Right, square of opposition. In this lesson, we'll be investigating the relationship between four different syllogisms about arbitrary groupings C and D. All C are D, no C are D, some C are D, some C are not D. Here are the Venn diagrams for the first three of these syllogisms. Okay. Here are four possibilities for the last one. Some C are not D. Which is the correct diagram for some C are not D? Some C are not D. So some has to be a tick instead of a check. So it can't be this. So some C, well, that's some D. So some C are not D, yeah. And this is some random stuff that aren't C or D. So it's number 3. Okay. We're going to use these four statements to make a square of opposition that relates all four. The concepts here go back to ancient times and the work of Aristotle. The blank portion of statements will be filled in as we go along. Okay. In the square of opposition, the four statements have special names. You do not need to memorize them, but they're given here for completeness. A statements, all CRD, are universal affirmatives. E statements, no CRD, are universal negations. I statements, some CRD, are particular affirmatives. O statements, some C are not D, are particular negations. So universal, particular, affirmations, negations. Okay. We'll need one extra special condition. Oh, great. Extra special. Which was used in ancient times. Neither category is empty. You can assume this for every logical statement that follows in this lesson. Okay. The statements are considered contradictory because exactly one of them is true at any time. Exactly one of them. So the other one can't be true. For example, A, all C are D, and O, some C are not D, are contradictory because all C are D, some C are not D, so they contradict. What is contradictory to E, no C or D? I, obviously. It shows us right here, check mark and tick. Some CRD. No CRD, some CRD. Okay. Thus the corners of the square of our square of opposition contradict each other. Okay. A pair of statements that cannot both be true at the same time, though they can be false at the same time, is called contrary, not contradictory. Okay. Which of the following pairs of statements is contrary? Right, okay. So a pair of statements that cannot be true at the same time, though they can be false at the same time. Right, let's have a look at this. So they can't be true at the same time. All CRD. So them two are true. No CRD. So these two aren't the same. So a pair of statements that can't be true at the both at the same time, though they can be false. So A and E can't be true at the same time, but they can both be false at the same time. I think. No. No CRD, all CRD. Can they both be false at the same time? You know what, I don't know. My head is hurting. A pair of statements that cannot be true at the same time, though they can be false at the same time, is called contrary. Some CRD, some C are not D. Why is this such a struggle for me? I don't know why my brain can't work this one out. Right, a pair of statements that cannot be true at the same time. What's the difference between contrary and contradictory? The fact that they can be false at the same time. I don't know why I'm struggling so much on this. So they're contradictory. No C or D, some C or not D. No C or D, some C or not D. I think that's fine. Some C or D, some C or not D. Hmm. All C or D, some C or D. That's weird. That's weird, that is. All C or D, so some C or D is obvious. But I don't, that's not contrary, I don't think. That's just obvious. So it's either this one or both of these. Pair of statements that cannot be true at the same time. Cannot be true at the same time. Wait a second, is it the top one? I'm really struggling with this. All C or D and no C or D cannot be true at the same time, though they can be false at the same time. How can they be false at the same time? No C or D. All C or D. Because if we go back up again, it said, somewhere anyway, the special thing. Here it is. We'll need one special condition when neither category is empty. And if this all CRD, no CRD is empty, then C would be empty. I still think that it's this one though. I'm gonna go for that one. Oh, nice. Right. I just don't understand how that can be applied while this special condition is applied. Or maybe it can't, and that's the whole point of it. I don't know. A pair of statements that cannot be false at the same time is called subcontrary. Which of the following pairs of statements is subcontrary? Can't be false at the same time. So if all CRD, this is a check. Some CRD, this is a check. So they can't be false at the same time because they've both got a check in. So all CRD, some CRD. All CRD, some CRD. All CRD, some CRD. Wonder if there's another one because we've got two of the above pairs. So no CRD. No CRD. Some C. So there's a chance that I might be able to get a check in here, cross in here. So no CRD and some CR not D. No CRD, some CR not D. So I think it's two of the above pairs. Oh, what? I got them both wrong. What was the question? Which of the following pairs of statements is subcontrary? A pair of statements that cannot be false at the same time is called subcontrary. Some CR D, some CR not D. Oh, I think my head's exploded. Some CRD, some CR not D. Right. Which statements? A pair of statements that cannot be false at the same time. A pair of statements that cannot be false at the same time. Right, is this what the special condition's about? Because if they were both false, then there would be nothing in C. I'm not sure. Let's have a look at the explanation. Making a statement false means that any check marks on the diagram turn into crosses, and any crosses turn into check marks. When crossed out, I think it causes category C to be completely crossed out. Yeah, that's the special condition that I was talking about. So that's why that one is not possible. I think I've misunderstood the question then. I wonder what I was doing. I don't know what I was trying to answer. I was trying to find things where there was two of the same, rather than two that were different. Right, yeah, I'm not quite sure what I was doing. My thought process obviously went down the complete wrong path. If A is true, all C are D, then which of the choices must also be true? If A is true, all C are D, then which of the choices must also be true? I think this was the thing that I was going down, the thought process. So this is the one where the two check marks are going to be the same. Some CRD. Incorrect. Oh, I clicked the wrong thing. That was the one I meant to click, some CRD. So I wasn't incorrect, I just clicked the wrong thing. Whoops. If E is true, no CRD, then O must also be true. If E is true, no CRD, then O must be true. Some C or not D. Is the converse true? That is, if O is true, must E be true? Right, let me see if I can get my head around this. I don't think so. Show explanation. Yeah, because that one could still be filled. Just because it hasn't got a check-in doesn't mean that it can't have a check-in, it just means that it hasn't got one. Right, okay. This is the complete square of opposition, subalternation, subcontrary, contrary, contradictory. Okay. I'm absolutely never going to remember that. Oh dear. For most of the steps, we utilize the fact that neither category was empty. If that isn't the condition, as is often the case for modern logic, the only relationship that holds from the square of opposition is contradiction. Okay. So if any of these are empty, none of the rules apply. Okay, fair enough. Right, it's looking like I've got two more groups of questions in this category. So I think I'm going to call it an end to this episode, and then we'll finish this off in the next video, because my brain is, I don't think my brain can cope with anymore. So yeah, that was tough, that was. It was very easy at the beginning and then got incredibly difficult for my brain towards the end. But I hope you did better than I did. Let me know in the comments, and I hope you enjoyed it. Cheers for watching, take care, and I shall see you soon.